Hi guys, this is going to be our XY equilibrium demonstration. So follow along with the pink notes that you have and fill it out for the demo. So it starts out, chemical equilibrium is a dynamic system, meaning that the rate or speed that the forward reaction is occurring is at the same rate as the reverse reaction. So both reactions are happening at the same time. Reactants forming products forming back into reactants. They're happening at the same time at the same speed. Now, it doesn't mean that we have the same amounts of reactants and products. We could have a larger concentration of one or the other. We could favor the reactants or products, but they're both happening at the same time. So it says, even though a system is at equilibrium does not mean that the concentrations of the reactants and products are the same, as I said. A system at equilibrium can have more reactants than products, but the forward and reverse reaction rates are equal. So it's talking about the rate being equal. If a system is stressed, it will shift to relieve that stress. So what we mean by a stress is if we do something, we mess with that equilibrium, that reaction is going to proceed in the way to kind of fix it and get back to its equilibrium state. It will always try to get back to that. It's like getting back to its center of balance. So it says the purpose of this mini lab or demo is to determine how a chemical system will respond to stress and how that can be applied to every reversible reaction. The color in this system indicates the concentration of the reactants and products. If there are more reactants than products, the solution will be pink. You might want to underline that. More reactants equals pink. If there are more products than reactants, then the solution will be blue. So more products equals blue. If there are equal concentrations of reactants and products, the solution will be purple. So we've designed this reaction so that we have equal amounts of reactant and product. You can see our purple, kind of magenta, it's not super magenta, but purpley colored solution. The chemicals that we're dealing with here, it is a cobalt chemical that's giving us this purple, blue, pink color, and it's creating this very complex molecule, an ion. So we simplified down the reaction because we're just trying to analyze what direction the reaction is shifting and how it's relieving these stresses. So if you look at your reaction, it says X, the chemical X is represented by pink color. If we add hydrochloric acid and heat to it, those are our reactants. So X, HCl, and heat. On the product side, it makes Y, which is our blue tinted chemical, and water. So we are going to be adding some stressors to this reaction and seeing what occurs due to those stressors. Gotta keep an eye on my hot light. Okay, so we've got 4 different test tubes here. We're going to be testing each one of them with different things. You can see on your chart there it says the stress and then the initial color, final color, and shift direction. So we're going to start with this first test tube here on the left. Its initial color we can say is purple, starting out with that purple color. You can see that. And we are going to add about 10 drops of water to that test tube. So water in this case is a product, so we're adding more product to the reaction. You can always pause and kind of make a prediction what you think will happen. So here goes our water into that first test tube. So I've got a DI bottle, so I'm just kind of squirting some in. I'm doing a little more than 10 drops, but that's okay. And then I'm going to stir this, my stir rod here. Just need to wipe it off. And we can see that our solution has become more pink. So we added water, and now it's more pink. So that's our final color. Is that pink? You can see that we added a product, and we got a higher concentration of reactant because it turned pink. We've got a whole bunch of that pink chemical in there and less of the blue chemical. Remember, if there's equal amounts of pink and blue, it turns purple. Okay, so adding a product creates more reactants. All right, Our second stress, so we could say, sorry, let me make sure we complete that row. So our initial color was purple, our final color was pink. Our shift direction, so when we say this shift direction, we want to say which direction is in terms of the reaction, so left towards the reactants or right towards the products, is occurring. In this case, because we ended with a pink color and we have more reactants, it shifted to the left or towards the reactants. So you put that in that last column, to the left or towards the reactants. All right, now we're going to try our second one. So this is our second test tube here. And we are going to add really concentrated hydrochloric acid. So I have 12 molar here, highest concentration you can get. I know it just looks like water. Definitely is not. It's actually burning my sinuses. Stinks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, a couple more since I did with the water. Let's just make them equal-ish. Okay. I'm going to touch this. All right, I'm going to wipe off my stir rod here. Rinse it with a little water. It's a hard thing here because water it's in our reaction. We can't add more water here. Okay. So now we're going to stir this one. And this is one I really like. You get this beautiful cobalt blue from it. So we can compare it to our original purple. You can see it's definitely darker in blue. And you can see the little droplets on the top here. You get that nice, beautiful blue color. So there's some more droplets. All right. So let's take a look at our data table here. So we added 10 drops of HCl. So our initial color was purple. Our final color was blue. And our shift direction. So if we have more blue, that means it shifted towards that thing that's blue, so towards the products. So it shifted to the right or towards the products. All right. Doing great so far. So now we're going to actually set up our last two to run together. Our last two are in an ice bath and in a hot water bath. So I'm going to go ahead and set one of our test tubes. So you can do your ice bath one, starting at purple. We're going to set it down in this ice bath, and I'm going to grab the hot water. All right. Sorry, it took me a second. We'll grab our hot water bath. Okay, and we're going to put our second one. So again, here's our purple to start out with. Down into the hot water bath. And I'm just going to swirl these around. It says to do both for 5 minutes, but we'll probably see a change sooner than that. You might already notice a change. Okay. All right. Switch these back so we can take a look at them. So here is our hot water. We can see we get our nice blue color. And our cold water, we get our pink. All right. So let's take a look at our data here. So our ice bath for 5 minutes, third row, initially was purple. Final color, ice bath, is pink. Definitely pink. So the shift direction, we added, in this case, we put it in cold water. So it's like we're removing the heat. So we are shifting it towards that pink side. So we're shifting towards the reactants or to the left. So we're going actually towards the heat side, which is interesting. All right, so the other one, our last line, putting in the hot water bath, our initial color is purple. We've got our final color being blue. And the shift direction, if it's going towards blue, that means it's going towards the right or towards the product side. So now that we've got our demonstration and we've seen what happens, we're going to fill out the summary part at the bottom of your notes. So let me do a little adjusting here so we can line this all up. All forgive the thing here. All right, so increasing concentration. Our example of increasing concentration of something would be either of the first two stresses. We're adding a chemical, we're increasing its concentration. So if a reactant is added to a system, for instance, we added HCl in the second part of the demonstration, that's a reactant, the equilibrium shifts towards the products or opposite side. Okay? So when we added the HCl, on this one up here, we added more HCl, it shifted and became more blue, so it shifts towards the product side. That means that the amount of products is going to increase and the amount of our other reactant is going to decrease because we're using it up to create that product. All right, second part, if a product is added to a system, the equilibrium shifts towards the reactants. Again, it goes towards the opposite side. Okay, so our example of that was adding water. When we added the water, the solution became pink because it was shifting towards that reactant side and making more pink. And it was reducing the amount of blue chemical because it was using it up to make that pink. All right. Now the opposite of this, the decreasing concentration, when we don't have an example of that in this, but we can think through it. So it says if a, let's start with reactant, is removed from the system, the equilibrium shifts towards the blank. So let's think about this. If a reactant is added, it shifts towards the opposite side. It's going to push the reaction towards the opposite sides. If you remove something, it's like it pulls the reaction towards that to replace it. So it's going to shift towards the reactant side or the same side as the chemical you remove. So let's look at an example of that. So say I had this reaction and instead of adding HCl, I removed some of it. So I was able to pull that out and separate it out from the reaction mixture. That means that this reaction has less HCl than it used to have at equilibrium. So now it needs to replace it. It needs to make more. So for that to occur, the reaction is going to shift towards that HCl. It's going to go in the direction that creates more of that chemical. So it's like you created a hole here and you got to fill it up by going towards that side. So it's going to decrease the amount of our products. We're going to use those up. Increase the amount of our reactants. All right, so that also must be true for the products. So when we added a product, it shifted towards the reactants. So if a product is removed from the system, the equilibrium shifts towards the products. Again, towards the same side. So when we add something, it pushes in the opposite direction. When we remove something, it pulls in the same direction. Okay, so I kind of think of these as a push and a pull. Pull towards you, push away from you. All right, temperature. So we did temperature as well. So if heat is added to a system, the equilibrium shifts towards the blank. Okay, so let's look at this one. When we added heat, we put it in the hot water bath. That was our last one. We added heat, it turned blue. So it shifted towards the product side here. Now, it's because the heat was a reactant. It pushed away from it. If our heat was on the product side, it would again push away from it. So it will always shift towards the opposite side. Okay? So wherever your heat is, so we can, heat can be written on the reactant side if it's endothermic or on the product side if it's exothermic, as we looked at in thermochem. So it's always just going to shift towards the opposite. It's very similar to increasing concentration. You're increasing, think of it as increasing your concentration of heat. So again, this one is a push. Now, if heat is removed, so we put it in a cold water bath, the equilibrium shifts towards the same side. This one's like the pull, okay? So again, we put this in a cold water bath, or ice bath, and it turned pink. So if you look at our reaction, we took away heat. We reduced this amount of heat. It went down, so we have to get it back. So it shifted towards the pink side, and we got more pink, but it also replaced that extra energy that we needed, that heat. So these chemicals reacted, we got more of the chemicals on the left. All right. So those are the three that we can really kind of figure out from the demonstration. The one we can't is for gases only. This is dealing with pressure. Okay, gases only. So if pressure is applied to a system, the equilibrium shifts towards the blank. Okay, when we look and deal with gases, it has to do with the moles of gas on each side of the reaction. So I'm going to give an example equation here. Very common one we've looked at. Nitrogen gas plus 3 hydrogen gas make 2 ammonia gas. Okay, so if this is an equilibrium and we've got our double arrow, if we had all of this in the same container and it was at equilibrium and we added pressure, that means we add pressure. You can always think of pressure going up, causing our volume to go down, because those are opposite relationships of each other. So if we put more pressure on this, it's like we're smushing it all into a smaller container. So if we smush it all together, we want less particles there because we want them to take up less space. Okay? So it will always shift towards the side with less moles of gas. The equilibrium shifts towards the side with less moles of gas. Okay? So if we put pressure on this system, this side has 4 moles of gas total, this side has 2 moles of gas total, so it's going to shift in this reaction's case towards the right because we have less moles of gas. We're shrinking that down into a smaller container, and we want to have less overall particles. Okay? So this side we have 4 particles versus 2, so we want to shift towards that side with less. If pressure is removed from a system, the equilibrium shifts towards the side with more moles of gas. Okay. So in this case, if we can also think of this one as our pressure going down, then our volume is going to increase. We're spreading it out. So we want to take up as much space in that container as possible. So we want to shift towards the side with more stuff to take up the space. So in this case, we've got 4 moles on the reactant side, 2 moles on the right. So if we remove pressure from this whole system, it's going to shift towards the side with more moles of gas. Okay? So this overall summary is going to help us do our practice. I'm going to walk you guys through one so you know how to set these up on the next page. So turn to your next page where your practice is. We'll walk through some of this together. Adjust a little. All right, so our intro says, consider the equilibrium reaction PCl3 plus Cl2 makes PCl5. They're all gases. How would the following changes affect the partial pressures or amounts? You can think of their partial pressures as being similar to their molarity of each gas at equilibrium. Indicate the shift with an arrow, left or right, on the dotted line. So we're going to be putting arrows basically under the other arrows to show which direction it's increasing or which way it's shifting. And then indicate the chemical change for each. So an I for increase or a D for decrease. And X is used for the chemical that is already being described. So whatever chemical we're already talking about here, we're just going to put an X there because we already know what's happening to it. So let's take a look at the first one. We'll do this first set. I'll do it with you guys. I believe there's plenty for you guys to do. Okay, so we're going to add first PCl3. So we're going to put an X on the PCl3 line because we're already talking about that one. And then we want to think about which way it's going to shift. So we're adding more reactant. So anytime we add something, we want to push towards the other side. So we're going to push towards the right. Okay, it's going to shift towards the right, which means our amount on the right will increase. Okay, your arrow is always going to point to the chemical that's increasing, which means we're using up this extra PCl3 that we're adding and some of the chlorine that's already there to make this. So our chlorine is getting used up, it's going to decrease. Okay. So there's our first one. Our second one says removal of Cl2. So we're going to get rid of, we're going to be dealing with the Cl2. We're removing it. We're taking some of this away. So anytime we remove, we want to think, okay, we're pulling towards that thing. So we're going to go towards the chlorine. So that means our PCl5, we're using up that chemical or decreasing its amount to make more of the chlorine since we removed some of it, and it's going to make more of the PCl3, so that amount's going to increase. Okay. Next one, removal of PCl5, so we're going to put an X on that one. So we're taking it away, taking some away, so it's going to pull towards that chemical, which means if it shifts that way, we're going to replace the stuff that we removed, and we got to use up the chemicals on the left to make it. Okay, again, so your arrow always points towards the side that increases. All right, our last one, decrease the volume of the container. So volume down, which means our pressure goes up. Okay, so we are making a smaller space. Okay, we're going from a large container to a small container. So we want less stuff to fill up our container. So we want to push towards the side that has less stuff. So on this side, we have 2 moles of gas. And on this side, we have 1 mole of gas. So we want less stuff. So that means we're going to go towards the side with less moles. So again, this side's going to increase, which means the other side will decrease. Since we were talking about the system overall, we don't have to put an X anywhere. So that's going to be how you approach these. Remember, whenever you're dealing with pressure, only pay attention to ones that have gases. Ignore anything that's a liquid or a solid. If you're looking at something like our next one, where it has your delta H values separate, if it's positive, remember that means it's endothermic, it'd be a reactant. So you can put your plus heat on this side. If it's negative, it'd be on the product side. So keep those things in mind as you go through this. The other thing I will mention is we've talked about catalysts and how they affect reactions. So a catalyst will speed up the reaction. However, our reaction will still get to the same exact equilibrium it was at before. So adding a catalyst has no effect on the reaction overall, on its equilibrium. It just gets it there faster. Okay? So continue with the practice on that, and question marks next to any specific one.